Metabolism. It's the sum of all the chemical reactions it takes to sustain life. These reactions require energy, and energy allows work to be done. Let's explore the relationship between energy and work for a second. Energy is the capacity to do work. We'll discuss two forms of energy, potential and kinetic. Work involves applied force and distance traveled. Physicists have lots of formulas to explain those relationships, but that's way beyond the scope of our course. So finally, power. Power is the rate of doing work or the rate of using energy. But mainly, we'll be talking about just energy and work. Why do people care about metabolism? Why should you care about these relationships? It's because the more work you do, the more energy you consume. It's the exact reason why people exercise to lose weight. Energy consumption for metabolism is one of the characteristics that all living things share. That's why we spend so much time talking about metabolism and energy consumption in biology class. Let's take a moment to distinguish between potential and kinetic energy. Put simply, kinetic energy involves movement, and potential energy involves resting objects with the capacity for work in the future. So here we go. We've got high potential, then moving, and then we've got back to potential. Remember that kinetic is moving. So the primary forms of kinetic energy that biologists are concerned with are the electromagnetic forms, specifically the visible spectrum, which is the light spectrum that we can see, and thermal, which is the heat. So light and heat are both forms of kinetic energy. The form of potential energy we'll concern ourselves with is the chemical form, the energy that's stored in bonds. So there we've got potential energy in those organic molecules of that wood there. That can be transferred to kinetic energy. But other forms of potential energy are gravitational, mechanical, and nuclear energy. So we won't talk much about those in biology, but they are potential energy forms as well. You all saw my demo of the pennies with potential energy. As I held the pennies up, they had gravitational potential energy. When I tipped the bowl, that energy was converted into sound and motion. That brings us to the first law of thermodynamics. Energy can undergo conversions, but it cannot be created or destroyed. Energy in living systems tends to end up as heat through the process of metabolism. Remember this? The 10% rule states that 90% of energy is lost to heat created by metabolic work as you move from one trophic level to another. Lucky for us, the sun provides a constant supply of kinetic energy, and photosynthesis can capture that energy and convert it to chemical energy. So you got 90% heat loss, but input from the sun. Do you remember the name for the organisms that conduct photosynthesis? There was one big overall term, and that was the photoautotrophs. So here's the process of photosynthesis. So you can see that light is powering the synthesis of those organic compounds, high in energy, high in chemical energy. And that glucose, then, there's a reverse process, cellular respiration, to break it down and release energy in other forms, specifically ATP and heat. It's a little hard to see there, but it's there. Let's go back to the pennies. What did I cheer as they crashed to the floor? That's right, entropy. It's the second law of thermodynamics. Things tend to move from maximum entropy, or things tend to move towards maximum entropy, or that disorder or chaos. Picture a dog left to its own devices. Okay, so this dog could have been more destructive. That's more like it. That is really going to take a lot of energy to clean up that chaos. Energy conversion is a really inefficient process, and entropy is always going to be unavoidable. You'll see later that anabolic or synthesis reactions are balanced by catabolic or energy-releasing reactions. A single glucose breaking down is a catabolic reaction. You get physical products, but you get energy along with it. Thankfully, again, we've got the sun, which is constantly supplying more energy in a form so that living things can again generate that glucose, and this process can continue. Let's switch gears a bit. Most reactions release energy. They're going from high energy form to a lower, perhaps more stable form, but always lower in energy. These reactions are called exergonic reactions. They're releasing energy. They're also called catabolic reactions. So something like this is an exergonic reaction. So energy is released. These reactions tend to get hot. In organisms, though, often the products of a reaction are going to have more energy than the reactants used to build them. Like in photosynthesis, carbon dioxide and water don't hold a lot of energy in their bonds, but glucose does. They're absorbing free energy, and we call them endergonic reactions. So we've got our exergonic reaction and our endergonic reaction, and those are also called biosynthetic or anabolic reactions. When you look at this diagram that's tracking the free energy in the system as a relationship to the duration of a reaction, you can see that exergonic reactions, as they go along, have to absorb some amount of energy before forming products. That is called the activation energy. Endergonic reactions do this as well. So there's the activation energy there. That activation energy often comes from collisions or heat. And that's all what form of energy again? Yes, it's kinetic energy. In our bodies, there's actually a cool thing going on between the exergonic reactions and the endergonic reactions. Because as an exergonic reaction is taking place, the energy it releases could power an endergonic reaction, and this is all called reaction coupling. In our bodies, it often involves a middleman, and that is the ever so humble and awesome ATP. And it's also very abundant, which is good, because we need it for these reaction coupling, synthesis, and catabolic relationships. ATP, once again, is short for adenosine triphosphate. The adenosine molecule here includes an adenine and a ribose. And adding 3 phosphates, you have a lovely example of one of the 4 macromolecules. Can you recognize the macromolecule? With only 1 phosphate here, you're actually looking at a nucleotide. And so this is just a modified nucleotide, so it is a nucleic acid. ATP will carry the energy from an exergonic or catabolic reaction to an endergonic or anabolic reaction. That could be like the motor proteins here, or the sodium-potassium pumps, or the phosphorylation going on within enzymes. ATP is constantly regenerated from ADP and an inorganic phosphate. The phosphate group is called inorganic because it doesn't have any carbon-hydrogen bonds in it. The ATP-ADP cycle and the amount of potential energy that can be released is very close to the amount of energy required to reattach the phosphate to the ADP. This system is marvelously efficient when you consider the law of entropy and other thermodynamic properties. How is it so marvelously efficient? Well, first, the 3 negative phosphate groups can be very unstable. So by phosphorylating or adding a phosphate to another molecule, the resulting products, when you hydrolyze that, the ADP and the inorganic phosphate, are much more stable, and some of their potential energy is converted into kinetic energy that drives work. The last thing to address before we move on to enzymes is that catabolic reactions involve breaking down large molecules to form smaller ones, and that releases energy. A great example of this is cellular respiration. It does create ATP. But when I think of the term catabolic, I'm often thinking of catastrophe. So I'm thinking like big building, and a catastrophe tears it into little pieces and brings it down. So that's what helps me remember big to small is catabolic reactions. Anabolic reactions are what living things use to build complex molecules. You may have heard of anabolic steroids or hormones. Don't think you have? Well, I'm sure you've heard of testosterone and estrogen, and among their many functions, they signal cells to build bone mass or muscle mass. They are anabolic, building. Photosynthesis is also anabolic. So the anabolic reactions are consuming the ATP, and the catabolic reactions are building it back from those larger molecules, and they're breaking down. So it's a constant energy conversion cycle.